Good morning. This is class 12 of our chapter digital filters. Now, this section deals with the design of FIR filter using rectangular window. Now, this is probably asked as an essay question, that is design of FIR filter using a rectangular window. So, I have briefed some of the main points. So now let's begin. So suppose that you have a desired frequency response HD omega, and let the unit sample response corresponding to this frequency response HD omega be h of d omega n. So capital H of d omega is the desired frequency response, and corresponding to that we have a unit sample response given by HDN. Now these two are related by a Fourier transform relation of this form. So from this we can find out this unit sample response HDN by using integration, that is by using this particular equation. Okay, so if you have a frequency response given as HD omega, from that you can find the unit sample response H of dn using this equation. Now this unit sample response that you get, that is HDN, is actually infinite in duration. But if that unit sample response is infinite in duration, then it will be very difficult for us to calculate. Okay, so in order to make the calculation part easy, what we have to do is we have to truncate it, that is we have to make that infinite the sample response into a finite one, that is we have to limit its length. For that what we do is truncation, that is it is limited to a finite duration, say of the order of m minus 1, where m is actually the length of the FIR filter. So this unit sample response HDN is infinite in length. So in order to make it finite, that is in order to restrict it to a duration of m minus 1, that is where m is the length of the filter, we are using a process called truncation. Okay, now this for that truncation, what we do is we are multiplying that unit sample response with a window function. Usually for calculations we are using various types of windows are available, but for making our calculations easy we are using the rectangular window function. Okay, now so that is done here, and now so this truncation is done first, and then we are multiplying it with a rectangular window, and that rectangular window is of the form Wn. It is represented like Wn, and it has got value 1 when in the value of n is from 0 to m minus 1, and all other cases it will have a value 0. Then the unit sample response will be like this, that is this unit sample response multiplied with the window function Wn will give you the actual unit sample response of the FIR filter Hn as this, and these are its values. Now this multiplication of this window function Wn with HDN is equivalent to the convolution of HD omega with W omega, where this W omega is the frequency domain representation of window function, and it is given by that integral summation. So the convolution between this HD omega with omega W omega is given by this particular equation. Now now we have to study two expressions for rectangular window. Now the one expression that you have to study is that of see the Fourier transform. Two expressions you have to study for rectangular window. For rectangular window, the Fourier transform of rectangular window is given by this expression, and the magnitude response of rectangular window is given by this expression. Okay, so these are the two expressions that you have to learn. that is the Fourier transform and the magnitude response of rectangular window. This particular expression, I think you can skip, no need of learning that. Now next one, we are going to learn about the magnitude response of window function. See, the magnitude response of the window function is here illustrated in this graph, and here the length of the filter M is taken to be 31. Now here the width of the main lobe, there are main lobes and side lobes. Here the width of the main lobe is found to be 4 pi m by m, where m is the length of the filter. It is seen that as the length of the filter, that is m, increases, the main lobe will become narrow, that is its width decreases. But whereas in the case of side lobes, the width of the side lobe will decrease with increase in m. So that is how this length affects the main lobe and side lobe. That is, as the length m increases, the main lobe becomes narrower, whereas the side lobes, that is the width of the side lobe, decreases with the increase in m. It is given in that paragraph. And what about the height of the side lobe? The height of the side lobe also will increase with increase in m. But that increase in height will be in such a way that area under each side lobe remains invariant. So as m increases, that is as length of the FIR filter increases, the main lobe becomes narrower, whereas the side lobe's width decreases with increase in m. And what about the height of side lobe? It also increases with the increase in m in such a way that area of each side lobe remains invariant. Okay, so these are the 3 points that you have to study about the effect of length of the filter on the width of main lobe and side lobe. No need of drawing the figure, just write those sentences. Now let us see the underlined portion, that is about the characteristics of rectangular window. It actually plays an important role in determining the resultant frequency response FIR filter obtained by truncating the unit sample response HDN to the length of the FIR filter M. Now this is figure actually shows the various type of window functions possible: rectangular, Hamming, Blackman, Hanning, etc. But rectangular window is most widely used. As already said, as this m increases, we can see that as m increases, W of omega becomes narrower, and the smoothing provided by this and the smoothening result in some undesirable, as the length of the filter, that is m, is increased, this window function will become narrower, and the smoothing provided by window function will get reduced. On the other hand, the large side lobes of the window function will give rise to some undesirable ring effects, and this will produce some discontinuities, especially in the time domain characteristics. Okay, so this is some of the effects of or the characteristics of rectangular window. Now this is just an example showing how to design a FIR filter using rectangular window. I think you can, if you want, you can go through this example. Otherwise you can skip this slide as well as the next slide, because these two slides actually deals with the example, that is it is giving us an example of how to design an FIR filter using rectangular window. So I think you can skip this slide as well as this slide. So these two slides deals with the example, so if you don't want, you can skip these two slides while you are writing essay. Now this paragraph actually deals with a phenomena that we come across while dealing with the design of FIR filter using rectangular window, that is called Gibbs phenomenon. It is called by the name Gibbs phenomenon. See, this is Gibbs phenomenon. Okay, now what is Gibbs phenomenon? Let us see. Now we observe that large oscillations or ripples will occur near, especially near the band edge of the filter, and these oscillations thus developed will increase in frequency as the length of the filter M increases, but they will not diminish in amplitude, that is, they will remain as such. So such oscillations when produced are actually, these oscillations are actually the direct result of large side lobes existing in the frequency characteristics of rectangular window. So how these oscillations are arising, because we have already seen that in rectangular window there are side lobes and main lobes. So because of the existence of side lobes, some oscillations will be present, especially near the band edge of the filter, and these oscillations naturally increases as the length of the filter increases, but their amplitude will not diminish, that is, their amplitude will remain as such. Now the truncation of Fourier series, we know the series obtained will be infinite. So in order to for making the calculations easy, we are truncating it to a finite length. So that truncation is known to introduce some ripples. That truncation process also will introduce some ripples or oscillations. And this will actually lead to the non-uniform convergence of the series at a discontinuity, or this oscillatory behavior near the band edge of the filter is called by the name Gibbs function. So in briefly, if you are asked to write what is Gibbs function, then you can say that because of the presence of large lobes in the rectangular window, and also because of the truncation process, it is possible that some oscillations will develop, especially near the band edge of the filter. These oscillations thus developed will increase as the length of the filter increase. However, their amplitude will remain the same, that is, the amplitude will not diminish, and these oscillations thus developed will produce a non-uniform convergence of the Fourier series at a discontinuity. The oscillatory behavior near the band edge of the filter is thus called by the name Gibbs phenomenon. This is what that you have to write if you are asked a question like explain the Gibbs phenomenon. Okay. Now this is the last slide. This actually shows the frequency response of rectangular window. That is, you can see large oscillations in both passband and stopband. So we will be using a window function, that is rectangular window, that contains a taper and decays toward zero gradually instead of decreasing abruptly as it occurs in rectangular window. So this is how the frequency response of a rectangular window will look like. So this graph, I think you can just learn a rough sketch of this. Okay. So as illustrated in the figure, the window function do indeed eliminate all the ring effects at the band edge and do result in lower side lobes at the expense of an increase in width of transition band of the filter. So while when you are asked to write an essay question, that is explain how to design an FIR filter using rectangular window, you can start the beginning of this slide, and about this slide also, that is how you are truncating a series and how you are multiplying it with a rectangular window function, everything. Then write the expression for the Fourier transform and magnitude response of rectangular filter, rectangular window. This piecewise linear phase, no need of writing. And this one, that is the effect of length of the filter on the main lobe and side lobe, you can write. Then the characteristics of window function, the rectangular window function. And this slide you can skip, no need of writing. If you want, you can just go through, that is enough. This slide also you can skip, because these two slides leads with the example, so no need of writing it in the essay part. Now we are explaining the Gibbs phenomenon in this slide, and finally we write the frequency response of the rectangular window. So that's all for an answer to the essay question. Okay, thank you.